Hi, I'm Randall Heyman. You're watching one of my Corona Help videos. If you'd like me to make a video for you, then just comment below any of my videos or drop me an email. So I got an email from Andrew, who's contacted me before, and he was asking for some intuition about this, this statement here, which is called Gauss's lemma, although I should just warn you that there are different lemmas that are called Gauss's lemma to do with this area, but there's a bit of a vagueness about what is and is not Gauss's lemma, so just be careful of that. Anyway, let's just read through this. So we have it saying if a polynomial in Zx, so that's just a polynomial with integer coefficients, for example, x squared plus 6x plus 10, that's an element of Zx. If it's reducible in Qx, then it's reducible in Zx. And Qx, so what's Qx? Something like x squared plus 6x on 7 plus 10x on 11. That would be an element of Qx. Okay, so now Andrew's worked through the proof, and the proof, the standard proof, in fact, it's the only proof I know, involves the concept of a primitive polynomial. So what's that? That's if we've got some polynomial that goes down to A0, where all the coefficients are integers. So this polynomial is a primitive polynomial. If the GCD of AN of all the coefficients is equal to 1. Now, some of you, look, I guess everyone who's looking at this will understand how you can have a GCD of more than two numbers. In school, you have the GCD would be two numbers. In this case, it's n+1 numbers. So the GCD there is just, you just follow what GCD means. We're looking for a divisor of all of those n+1 numbers. The divisor must be common to all of them. And if there's more than one, well, we're interested in the greatest one. So in this case here, we're saying that the only divisor basically is 1. So this one up here would be primitive because the GCD of 1, 6, and 10 is in fact 1. Okay, let me rub this out from the previous video. Okay, so where's the intuition? Look, the first thing I'll just say very briefly, if you start looking at something that's reducible in Qx, I don't know, something like, let's take 3x on 5 plus 7/8 x plus 11/12. So that's reducible in Qx. If it was going to be reducible in Zx, so let's, reducible in Zx. Well, the only intuition here I could say is that you can see that you're going to be, once you get some expression that involves the z's, you can see that it's somehow going to be linked to this concept of the GCD either being 1 or not being 1. That's not really a good explanation, but if you just play around with it a bit, you'll see, you may well get some intuition that that this GCD is important. And so there's this concept of the primitive polynomial. But I think the best insight you can get is to go back up to here and play around with, well, use the contrapositive. So in fact, what I'll do is I'll rub all this stuff out now, because I want to just use this So if you're confused by the contrapositive, that just says, like, if we've got a statement, if A, then B, that is the equivalent of if not B, then not A. If you have trouble with that, have a look at my video, Proofs Made Easy, where I go through all the standard sorts of proofs, and the contrapositive is one. So what we can say is that the above is equivalent to if a polynomial in ZX is, now I'm not going to write not reducible, I'm going to say is irreducible in ZX, then it is irreducible in QX. Now, why do we want to do that? Well, the first thing that comes to mind is it shows you the real power. It reveals, so it reveals the power of Gauss's lemma. So what do I mean by that? Well, this is saying that if something's irreducible, if we prove that something's irreducible in here's ZX, well then we get this for free. So you might be doing some mathematics and you prove that, well then this gets you that for free. If you ever have to prove that something's irreducible in the QX, well then it just suffices to do it in ZX. So that's part of the reason why it's better to turn around. And then I suppose, look, if you wanted to, you could start to explore this statement here, just using an example. It's not going to get you to a total feeling for the proof, because the proof relies on that primitive polynomial. So unless we're going to start going down that path, you're not going to see you're not going to be able to really get to the total proof. But I mean, you could, if you wanted, sort of look at that one we had before, x squared plus 10, x squared plus 6x plus 10 is irreducible in ZX. Why? Well, the discriminant, which is 36 minus, so it's b squared minus 4ac, so minus 40 equals minus 4 is less than 0. So we're going to have complex roots. So it's not going to be reducible in ZX. So what you could do is say, well, imagine or suppose this is contrary. Suppose it is reducible in QX. So what you could do is you could say something like, I was just playing around this with before, you could say it equals AX plus B times, so we want the coefficient of x squared to be 1, so this would be x on A, plus this would be 10 on B. That gives us the 10 at the end, the constant coefficient, when we multiply B by 10 on B. And here, I suppose you'd need that I don't know, I'll leave you to play around with. One of A and B is not an integer, but both A and B are rationals. And then you'd probably want something here about A and B not equaling 0. And if you do that, well, if we go back up here to the 6, so we need the coefficient of, so coefficient of x is 6. So what does that mean? A on B plus B on A has to equal 6. So A squared minus 6ab plus b squared has to equal 0. And then you can just sort of play around with it from there. But you know, I don't think you're going to make much progress. I don't think you're going to get a lot of insight, but you could go down that path. But I think the main thing is to maybe think about it in this term, because then it's as I said, it's really how you're generally going to use it. Okay, that's all I wanted to say there on the insights. Any questions, let me know. Otherwise, I'll stop here.